In today's video, we're going to look at applications of the integral in business and economics. So there are three things that we will study in this video. We will look at income streams. So we'll look at how to find future value of an income stream as well as present value of an income stream. We will then look at producers and consumers surplus. And we will end by looking at the Gini Index. So let's consider a firm generates a stream of income over a period of time t. As the income is realized, the firm reinvests it, and then it earns interest at a fixed rate. The accumulated future income stream is the amount of money the firm ends up with at the end of the period. Let's say we want to find the total future value of this income stream. What we're going to do is we're going to say let R of t represent the rate of income generation at time little t. Little r will be the interest rate that is compounded continuously. And capital T will represent the term of the income stream. What we're going to do is divide the interval 0 to capital T into capital N subintervals. Each subinterval has equal length delta t, which will of course be capital T over capital N. Now, assuming that R is continuous, we can say that R is approximately constant on each subinterval if delta t is small enough. So for small enough delta t, we can treat R as a constant over each subinterval. So the income generated over the ith subinterval will be R of t sub I times delta t. And this is income generated over the ith interval. Future value of this amount t years from now from our compound continuous formula, R of t sub I delta t times e to the little r t minus t sub I. And so this is future value t years from now. for the ith interval, then obviously the total future value will be approximately the sum of all these future values. Right? So A, not equals, will be approximately the sum I equals 1 to capital N R of T sub I e to the R capital T minus T sub I delta T. Using properties of exponents, we can write this piece as e to the RT times e to the negative RT sub I. And that allows us to write the sum now as e to the R capital T, since that is constant with respect to the sum. I equals 1 to capital N, R of T sub I, e to the negative RT sub I, delta T. Now this is a Riemann sum. And obviously, this approximation becomes better and better. So approximation becomes better as we let n go to infinity. Right? So if we let n just keep growing, this becomes a much better approximation, and in fact, it will converge to the true future value. Also, since we have a Riemann sum, that Riemann sum will converge to an integral, and so we get this result. The accumulated or total future value after t years of an income stream of R of t dollars per year earning interest at a rate R per year compounded continuously is given by A equals e to the R times capital T times the integral from 0 to capital T, R of t, e to the negative R little t, dt. Now the present value of an income stream is defined as the, don't know what happened, as the principal that will yield the same accumulated value as the income stream itself when invested today for a period of t years at the same interest rate. Right? In other words, if P is our principal, then P e to the RT is equal to e to the R capital T times the integral from 0 to capital T, R of t e to the negative rt dt. All we have to do is solve for p by dividing by e to the r. I forgot. That should not be a little t, that should be a capital T. And by dividing by p, dividing both sides by e to the rt. This will give us this result, the present value of an income stream of R of t dollars per year earning interest at a rate of little r per year, compounded continuously is given by capital P equals the integral from 0 to capital T r of t e to the negative rt dt. As our example, starting at age 25, you deposit $2,000 a year into an IRA account, an individual retirement account. Treat the yearly deposits into the account as a continuous income stream. If money in the account earns 10% compounded continuously, how much will be in the account 40 years later when you retire at age 65? And then how much of this will be just interest? Then we'll look at what would happen if you had waited 5 years to start the deposits. That is, instead of starting at 25, you started at 30. I'll write down what we know. R of t is $2,000 per year. The term will first be 40 years. The interest rate is 10%, so 0.10. Then the accumulated amount will be e to the 0.1 times 40 times the integral from 0 to 40 of 2,000 e to the negative 0.1 t dt. This will be 2,000 e to the 4 times the integral from 0 to 40 of e to the negative 0.10 t. Okay. Now this is a u substitution. We're going to say u is negative 0.10 t, which means du is negative 0.10 dt. Since we do not have a negative 0.10, we're going to need to multiply by it and then also divide by it. That will make this negative 10 times 2,000 e to the 4th times the integral 0 to negative 4 e to the u du, which we know is negative. Actually, I'm going to use a property here and say this is 20,000 e to the 4th times, from negative 4 to 0, e to the u du. Right? Remember, we're allowed to do that. Multiplying an integral by a negative just flips the bounds. This is then 20,000 e to the 4th times e to the u evaluated from u equals negative 4 to 0, which is 20,000 e to the 4th times e to the 0, which is 1, minus e to the minus 4. And when you evaluate this, we get about $1,071,963. Now, the amount of this that would be interest. So this is what it would look like at retirement. You'd have over $1 million in retirement. The amount that is interest, we would take this accumulated amount and subtract out how much we deposited, which would be $2,000 a year for 40 years. That winds up being $991,963. So of the just over $1 million in the account, just about 992,000 of that was interest. If instead we waited 5 years, then we'd only have it for 35 years. So A would be 2,000 would be 20,000 e to the 3.5 times e to the u, evaluated from u equals now negative 3.5 to 0. Right? It's the exact same formula as up here, except we replace 40 with 35. This would be 20,000 e to the 3.5 times e to the 0 minus e to the negative 3.5, and that is approximately $642,309.04. In other words, waiting 5 years will cost us about $430,000 in retirement. And that's just waiting 5 years. Imagine if you had waited 10 years, how much money you would lose. Looking now at consumers' surplus. Suppose that P equals d of x is the demand function. That relates unit price P to the quantity demanded. Let's suppose that P bar represents fixed market price per unit, and that X bar represents the units demanded at price P bar. Well, and what this means is those consumers who would be willing to pay a unit price higher than P bar would, in effect, experience a savings. This difference is what's called the consumer's surplus. So the difference between what they pay for it, P bar, and what they would actually pay for it is your consumer's surplus. So the interval we're looking at is 0 to X bar. So we divide that interval into n subintervals of equal length. Call it delta x, which is X bar divided by capital N. Then, for number of units between x sub I minus 1 and x sub I, there are consumers willing to pay D of X sub I per unit. So the savings these consumers experience can be approximated by D of X sub I delta X minus P bar times delta X, right? The amount that they would have been willing to pay minus the amount that they actually paid. This would be D of X sub I minus P bar delta X. Total savings then, let's call it the total consumer surplus, is approximately the sum of all of these, right? So I equals 1 to N D of X sub I minus P bar times delta X. Right, that'll be the sum, I equals 1 to N D of X sub I delta X minus P bar delta X. Or rather, no, yeah. Splitting this up, we can write this. P bar delta X is constant, so that just becomes P bar times N times delta X. And remember, delta X is X bar over N. So this is the sum I equals 1 to N D of X sub I delta X minus P bar times X bar. Now, as n approaches infinity, this becomes a much better approximation. Also, again, recognize that this term right here is a Riemann sum. Right, so as n approaches infinity, this approximation gets better. And we will wind up with this result. The consumer's surplus is given by CS equals the integral 0 to x bar d of x dx minus p bar times x bar d of x is demand, p bar is the unit market price, and x bar is the quantity sold at that price. Now looking at producer's surplus. We're going to say P equals S of X is supply equation. This relates to the unit price P of a certain commodity to the quantity X that a supplier will make available. Once again, we're going to say that P bar is a fixed unit market price, and X bar is the units made available for P bar. Suppliers who would be willing to make the commodity available at a lower price will then stand to gain from the fact that the market price is set at P bar. The difference between what the suppliers actually receive and what they would have been willing to receive is the producer's surplus. We would use an analogous argument to what we did for consumer surplus. So we're going to skip that derivation and just jump right to the result. The producer's surplus is given by P bar X bar minus the integral from 0 to X bar S of X dx. Right, again, S of X is supply function. P bar is unit market price. And X bar is quantity supplied at P bar. Looking at a couple examples. First, we're going to find consumer surplus at a price level of $8 for the price demand equation 20 minus 0.05x. All right, first, we need to find X bar. Well, P bar would be 20 minus 0.05 X bar, right? X bar is the demand at P bar. But P bar is 8, so 8 would equal 20 minus 0.05 X bar. Now we just solve for X bar. Negative 12 is negative 0.05 X bar. And so X bar is 12 over 0.05, which is 240. This is our X bar for our equation. Consumer surplus is then the integral from 0 to 240 of 20 minus 0.05x. Now, what we're going to do is if we look back at the consumer surplus right here, another way we could write this is the integral from 0 to X bar d of x minus P bar dx. And that is what we're going to use down here. Minus P bar dx. Right? So then we're going to have the integral from 0 to 240 of 12 minus 0.05x dx. Again, fundamental theorem of calculus, we're going to have 12x minus 0.05 over 2 x squared. E value from x equals 0 to 240. If you plug this in, this will give us $1,440. This is our consumer surplus. Now let's look at this. We want to find the producer surplus at a price level of $20, given the supply equation 2 plus 0.0002 x squared. Again, we need to find x bar, which is found by the equation P bar equals 2 plus 0.0002 x bar squared. So 20 is equal to that, which means that 18 is equal to 0.0002 x bar squared. This means that 90,000 is equal to x bar squared. And so x bar itself is 300, right? X bar has to be a non-negative value, so that's why we can ignore the negative 300. We can now just plug this into our producer surplus equation. Integral from 0 to 300. Now again, as with consumers, another way we can write this is the integral from 0 to x bar, p bar minus s of x dx. And that is exactly what we will do here. It'll be 20 minus the quantity 2 plus 0.0002 x squared. So it's the integral from 0 to 300 of 18 minus 0.0002 x squared dx. We get 18x minus 0.0002 over 3 x cubed. Evaluate from x equals 0 to 300, and that gives us $3,600. That is our producer's surplus. We now finally look at what's known as the Gini Index. So one method that is used by economists to study the distribution of income in a society is based on a Lorenz curve. What we're going to do is we're going to say f of x will be the proportion of the total income received by the poorest 100x% of the population. Obviously, x will be between 0 and 1. If we consider y equals x, then this means that exactly 100x% of the total income is received by the lowest 100x% of income recipients. Right? Then we say that this curve represents line of complete equality, meaning that the income is equitably distributed. Now, the closer a Lorenz curve is to this line, the more equitable the income distribution is among the recipients. Right? So the basic idea is we have something like this. That is our line y equals x, and then we'll have like a Lorenz curve, which generally is something like that. This area is going to represent the difference in distribution. Right? So the idea is the closer this curve is to y equals x, the smaller the area between them. So what we can do is we can define a number called the coefficient of inequality as the ratio of the area between the line of complete equality and the Lorenz curve. Now, if we look at the area under y equals x, this is a equals the integral from 0 to 1 of x dx, which is x squared over 2 evaluated from 0 to 1, which is a half. So the area under y equals x is 1/2. We get the following result. The coefficient of inequality, also known as the Gini Index, of a Lorenz curve is, we call it L equals twice the integral from 0 to 1 of x minus f of x dx, right? It's the area between x and f of x, which was this piece right here, divided by 1/2. Now, the smaller this number is, the more equally divided, or the more equally distributed the income is among a population. The larger it is, the less equally distributed the income is among the population. Now we look at our final example. Oops, wrong color, sorry. Lorenz curve for the distribution of income in a certain country in 2017 is given by x to the 2.6. Economists predict that the Lorenz curve for the country in the year 2030 will be given by x to the 1.8. We are asked to find the Gini index of income concentration for each curve and then interpret this. In 2017, the Gini index will be L equals, let's call it L sub 17, 2 times the integral from 0 to 1, x minus x to 2.6 dx. This is 2 times 1/2 x squared minus x to the 2.6 plus 1 over 2.6 plus 1, evaluated 0 to 1. Now this is 2 times 1/2 x squared minus x to the 3.6 divided by 3.6. And again, that is evaluated from 0 to 1. And this will give us about 0.444. In fact, it's 0.4 repeating. So that is the Gini index in 2017. In 2030, let's call it L sub 30. This is the integral from 0 to 1. 2 times the integral from 0 to 1. X minus x to the 1.8 dx, which is 2 times 1/2 x squared minus x to the 1.8 plus 1 over 1.8 plus 1, evaluated x equals 0 to 1, which is 2 times 1/2 x squared minus x to the 2.8 over 2.8, and that is, again, from x equals 0 to 1, and that will give us approximately 0.286. Now notice, if this is correct, then L of 30 is less than L of 17, meaning that if correct, in 2030, the income will be more equally distributed. Because again, remember, the smaller the Gini index, the more equally distributed the income is. And that concludes this video on applications of the integral in business and economics. This is also the end of the final video in this calculus techniques and applications series. I hope you have enjoyed this series and that you've learned something from it. And I wish you luck in any future endeavors that you may have.